Okay, so we'll get started. There's a smaller number of people here, but hopefully others will dribble in and aren't all sick like some of us have been struggling with. Okay, so today's discussion, we're going to be finishing up our discussion of Spark streaming mechanisms with two additional coverage. I alluded to one of them last time, and this is the use of filtering mechanisms built into Spark streaming for Twitter. So the idea is Twitter offers an API for subscribing to tweets. By default, that API for Spark streaming gets all tweets, or sorry, a random 1%, roughly representative 1% sample of all tweets worldwide. And you can receive them and filter them on your side. The challenge with that is that the 1% sample, while fairly representative, misses 99% of tweets. And often your interest, well, the 1% sample, I should note, is in large part motivated by the need to conserve bandwidth by Twitter. There's something like 8,000 to 10,000 tweets per second that come out of Twitter. And if they were to open the entire fire hose to streaming clients, amongst other things, it would impose formidable and infeasible bandwidth requirements. Hence, they limit it to 1%. However, for a given interest in Twitter, say to monitor certain keywords, to monitor certain location areas. While we could pursue that with looking for things in certain regions of location, certain geographic regions, or certain keywords within the 1% sample, it's not very efficient at all. Because that 1% sample, we've lost 99% of those that probably fall within that geographic region or that include that keyword. What's much more efficient is to use what's called, or what is sometimes called the filtering interface for Twitter streaming in Spark streaming here. And what this will involve is setting up a stream explicitly with Twitter that is configured to specifically send tweets that match certain criteria, okay? To send tweets, in our case, that will fall within a certain geographic region. In other cases, you may want to have a filter that specifies certain keywords. In other cases, you might want a filter that specifies certain users you want to follow. And in fact, you can do combinations of those. So you can look at those within a certain region that have certain keywords, for example. So this sort of interface that we're going to be looking at will support up to 40 bounding boxes, up to 40 sort of rectangles of latitude, longitude, one of which will be sufficient to describe our fair province. It also supports up to, I think, hundreds of users and dozens to hundreds of keywords. Okay. So it's a disjunctive thing. So you can look, does it get this keyword or that keyword or that keyword? It doesn't match regular expressions, but you can look for things that are smaller than the regular expression that are included in the regular expression, and then filter them by regular expressions once you get them. So this is much more efficient than getting the 1% sample and filtering that, because you can get a much bigger set of tweets for your region or your interest. So that's one of the topics we'll be talking about. And to do that, we're going to need to use a more recent version of Spark, okay, 2.2. And hence, we're going to have to log into that site. A second major focus for today is going to allow us to work in Zeppelin. And this concerns the management of state within Twitter streaming. Now, you may wonder, why is this such a big issue? Why? I mean, managing state is something every program needs to do. Why is it that it's particularly complicated with Twitter streaming, and Spark? Well, the issue can be boiled down at its essence to the following. Number one, Spark programs as a whole run across many machines, many different machines. They can run across hundreds or thousands of machines quite scalably. Number two, with streaming, you have to update that state as new data comes in. You have to somehow update the state in response to a new piece of data. All right. And so it's sort of tied up with the handling of the data as it comes in. And there's a very big question. Well, how do you put those two together? How do you square those? In the sense that we need to handle this data as it comes in across hundreds or thousands of machines potentially. How are we going to effectively do that? How are we going to do it other than putting in place very cumbersome mechanisms to communicate among the machines to say, hey, I got another tweet of this type, or I saw another instance of this keyword. How are we going to share a single common understanding of how many cases of this keyword we've seen, or how many tweets we found that match this criteria that come from Saskatoon across all the different machines? This is not an easy thing to do using traditional mechanisms, but Spark makes it quite easy. So we're going to see mechanisms for handling state using Spark, okay, for accumulating over time as data comes in certain statistics about what we're seeing in a way that embraces the data on all the machines. And to do that, we'll need to make use of some notions that those here might have encountered in past courses on things like maintaining concurrency. So maybe in operating systems, or of course, if you ever took one on say parallel programming, you might have encountered notions having to do with synchronization of multiple threads, etc. And we'll see some of that comes in a little bit, but in a pretty straightforward way. Okay, so we're going to switch over to the screen view, but not until I undertake a task that I'm going to ask all of you to do. So as you know from our last lecture, I asked all of you to verify that you can log into cmpt898.usas.ca with your NSIDs. And I'd like you to go do that. And I'm going to do the same. And while the internet will be relegated to look at my mug here, I am going to paste in my secret credentials there so that they don't appear throughout the bowels of the web. Okay. So here we go. I'm going to go over and I'm going to SSH to cmpt898.usas.ca. Okay. I'm just doing this. And there I am. You folks will have to log in. Oh, remember from last time, you may need to do SSH. We don't need the -X because we're not going to be using X, but your NSID at that, and the NSID at that will tell it the username you want to log in, and then it will ask you for your password. Okay? Having done that, I am going to remind you where our Spark shell is. Okay, there's a thing called Spark shell. This is how you started a traditional Spark installed on machine. There's a thing called Spark shell, and Spark shell on this machine is going to be located. I believe it's in. Okay. I think it's in user local. Is it user local? Why am I? Is it user share Spark? No. User I don't,
local Spark.
Spark. Oh, slash Spark. No.
No, Spark dash 2.2.1.
That's what I was thinking, but
It's not completed.
no. Okay. This is. Oh, wait. I did it to Scorpio. Why did I do it to Scorpio? That's weird. Okay. cmbda898.uss.ci. I just logged in the wrong machine. Sorry. Locate Spark Shell, and it'll tell us where it is. There it is. So thank you, Wade. So ladies and gentlemen, we're going to start up the Spark Shell. Okay. If you do locate Spark Shell, we'll tell you where it is on that machine, and use the first one. And I'm going to go invoke this. Here it is. And it's going to start up. And amongst the things it's going to load in is Apache Bahir. And Apache Bahir is going to contain the Spark, here it is, Spark streaming Twitter. Okay, so this is an indication that it loaded it in via Maven. It made sure, Maven or IV or what have you, and it made sure that it's here. So here's Spark Shell. And while it won't be visible to all those over the internet, what I'm going to go do is enter my secrets on Spark, my consumer key and access token. So consumer key secret, access token, and access token secret. Remember we got those from the apps.twitter.com, developer.twitter.com before. I'm gonna go declare those here, so that we can get them out of the way before I bring the web in, okay? Now I'm going to bring the web, okay? Join me in welcoming it to our classroom, okay? There we go. Okay, so, oh gosh, now I'm in trouble. Now I'm in trouble. Okay, now I have to do some editing. Okay, this is bad. Okay, so ladies and gentlemen, having pasted those in, I am going to then paste in some other elements. And fortunately, you don't have to worry about entering all these by hand. If you go to the Moodle site, those in the class, if you go to the Moodle site, you will find there's a file that I've posted there that is called Scala REPL 322 2008 March 22nd Spark streaming with location filtering on Moodle. And if you click on that, you can download it. And you will need to replace my credentials with your credentials, okay? Or else bad things will happen. It'll tell us, it'll say something like, you need more calm. Hold on, Turbo. It gives an error message, okay? Okay, now, so that's one element of what we need to do. We need to load in all these libraries. These libraries, as before, they include Twitter libraries for Twitter streaming. They include some Spark streaming libraries, and they include Twitter4j, which provides the requisite understanding of sort of Twitter constructs. Okay. So this includes things like filters, dates, users, tweet statuses, etc. And then we're loading in, there's a thing called atomic long, but we're not going to need it till the next one. I'm loading in a bunch of other libraries here. Okay. Now, including this Spark dates and time steps and arrays. Okay. Now, what I'm further going to do here is to go up and I will remind you how we entered in the information originally within Zeppelin. We found a better way to do it through interpreters. It's all done behind the scenes eventually in our current iteration. But this is how we originally did it. We said system.set property, and this was the property we want to set. And this is the access token. This is the string that would hold your access token. Replace it by yours, not mine. Okay. Similarly, this guy here and this property, etc. So having entered those in, we can now do this and, oh, okay, yeah. So, yeah, I think.
We do it again.
Well, I'll be, oh my gosh, okay, it's horrible. It just said what they were, but, okay, well, it's better than null. Okay, yeah, y'all have to do some editing on YouTube. Okay, so I had to do this twice. Nell pointed it out. I didn't remember that, but I guess it's a thing you're encountering as well. So, okay, next, we're gonna have a bit of code, and I'm gonna explain what this code does here. So, might as well just get this thing set up. There's a Spark streaming context here that will be set to go off every 30 seconds, okay? So every 30 seconds, we're gonna get a batch of tweets, a D stream of tweets, okay? Well, we're gonna get an element or an entry in a D stream of tweets. And the way Spark streaming will work is this D stream of status, it's going to be giving us to us in 30-second batches, and each of those status is going to denote a tweet. And we can ask about all sorts of information about that tweet from its status. Who sent it? How many likes has it gotten? Was it retweeted? Did we retweet it? When was it sent? What's the ID associated with it? What location, what place was associated? What geo coordinates? Like GPS location, if anything was associated with it. What is its text, etc. Okay. So that's going to be something we're going to get from a tweet stream. And we just set up a Spark streaming context, which tells us how often we're going to get it. Okay, the next little bit. Can you see my code here? And, do you have it as well? Okay. So the next little bit is just some code that's going to return a bounding box. This bounding box is going to specify our provenance, okay? And it specifies it in a way that's required by Twitter. Namely, it specifies it as a pair of the southwest corner and the northeast corner, okay? And if you were to go to Twitter documentation, and we were to go look at the Twitter API here, filter real-time tweets, and the API, you'll see where this is basically specified. So they say, okay, locations are specified as a pair of latitude, longitude pairs with southwest corner of the bounding box coming first, okay? So southwest, northeast. So this is for example, San Francisco. This is for San Francisco or New York City because it contains two bounding boxes. The first of them is for San Francisco. This is southwest. This is northeast. And then this latter one is for New York City, probably all 5 boroughs. Okay. Okay, so that's what we're basically doing here in this code. This code packs together this this array, and actually we get out a there's actually a little bit of finesse going on here. So we have an array of arrays here, and then we're passing it as successive arguments to this locations filter, which is something that's supported by by the Twitter for J. Okay. So this bounding box is going to give this array of arrays, okay, the southwest corner of the northeast. And I've given a little bit of margin here to avoid tweets from neighboring jurisdictions. I noticed if I got too close to the border, it would sometimes attribute tweets from the edge of Manitoba, maybe the paw, for example, to Saskatchewan, which if Wade had his location set as the paw, you know, but he were on his drive back to Saskatoon, that would, you know, it might catch his tweets. But in general, we don't want it, with nothing against the paw. But similarly, border things in Montana were being obtained, etc. So I put a bit of a buffer here, okay? Okay, now, after this, we're going to get a query. Now, this is where things get a little bit more flexible, okay? We're creating what's called a filter query here, and then we can apply a number of criteria here. We happen to only be exercising the locations one, but in fact, we could apply other criteria as well. And if you go to the Twitter for J documentation, if I were to go look here at Twitter for J, and I were to look at filter query, here we go. What you'd find is that it supports a number of different mechanisms. So, and these reflect what we saw earlier, the type of support offered within this Twitter API. They're using the Twitter API. So one of the things is user IDs we can specify, and there's a similar support here for people to follow, okay? So specify the users to follow. Now, there's two ways you can create these filter queries. One is to create all these at first. One is to call these things to set them. For some reason in the code, and I can't remember why, I ended up using the other, and it certainly worked. So I stuck with it, but you might be able to use the constructor for a neater way of doing it. The point is you can specify simultaneously keywords to track, locations to track, and that's up to 40 bounding boxes, I think, and people to follow, okay? And you can use all of these as supported by these kind of effective setters or with the constructor. So here, I happen to be creating one by locations, and that's using this bounding box here, okay? And if we were to look here for locations, okay, so I'm actually stand corrected. These are not independent args. Instead, what we have is these things are being marshaled as a single double. So things are being flattened into a single array of doubles here. There's a better way we could have done that. In any case, that's how we're getting the location. So I'm going to set the locations here. Oh, let's go copy those to our window here. This is setting the locations. So we're not tracking anyone. We're not following any user. We're not tracking any keywords. I should say we're just doing it by location. Okay, and we don't have any language restriction on this as well. Okay, so we're setting up a query, and the query could be by user, by keyword, or by location. And again, the important thing here to recognize is that we're doing this in an efficient way. It's Twitter that's only sending us tweets from that location rather than us taking this random 1% sample and only looking at tweets within the 1% sample that are from this location, okay? And similarly, we could tell it to only send us these keywords, etc. Much more efficient way of doing it. We get a much broader set of tweets from that. Finally, before we go into the next little component, we're going to create a filtered stream here. And for this, this is why we're using this in Spark 2. we're creating a filtered stream from this filter. Okay. And this filter is allowing Twitter itself to throttle what it sends to us. Yeah. And then from that, we're creating this place filtered stream. And I don't like that. We don't need that. We're not going to use it. I don't know why that's still in there. I deleted it last night. We don't need that place filtered stream. We're not going to use it. Okay. These things are actually already filtered to lie within there, and I'm not going to filter them further based on some criteria. The final thing we have to do is to set this up to be run. And I have here a little mechanism for doing this within an object, which is normally used to deal with synchronization problems. And we saw it last time because we couldn't synchronize one of the state variables. I actually don't see anything problematic about this. It's not clear to me why this is needed right now, because I don't see anything that it's depending on externally that would call a synchronization error. So I'm going to live dangerously. I don't ask you to do it right now, but I'm going to do this, and I'm going to execute this. And I believe we will be rewarded with simpler code and a bounty of tweets. Okay, but we will see our first tweet in 30 seconds, I think. It seems to be working fine. It would have complained about synchronization error. So you actually don't even need that in this case. I cleaned this code up from something much more complicated, and I evidently forgot to take into account that we didn't need. Okay, here we go. From Regina, from Saskatoon. You could see that Canadian politics is not unaware of U.S. politics. I believe they're referring to a certain president south of the border, but in any case, this is filtered by location. You'll notice that not all of them have the location in the stated place, I think. I think the place of this was given as Canada, but the tweet itself may have been geocoded to say that it's from L'Orange or from Swift Current or from Estevan or from Saskatoon. And so it got included. You have to understand that it's my understanding that, well, in general, for tweets, often we can find their location in several different ways. We can look at the location of the place associated with the tweet. We can look at the place associated with the user. We can look at whether the tweet is geocoded. And I believe Twitter may take these things into account too. So it's not basically just based on the tweet. It's based on several considerations, okay? But there's also a phenomenon that could be influencing this that I've got to warn you about, okay? And this is something that if you're working a lot with tweets and you're very sensitive to their geography, you're going to want to know about. I do believe there's an issue where if a tweet is from a jurisdiction that overlaps with Saskatchewan or with your jurisdiction of interest, your bounding box, if it overlaps with it, but it's not specific where within that region it lies, it'll say, well, maybe it could be in Saskatchewan, so it will include it. Maybe it could be in the bounding box. So let's take the city of Lloydminster. I don't know if any of you know, but Lloydminster is a city that's halfway. It's divided in half by Saskatchewan and Alberta. In fact, they have these big poles that go through it. And half of it is in Alberta and half is in Saskatchewan. So if a tweet was from Alberta, from Lloydminster, it would probably attribute it to Saskatchewan because it would say, well, it could be in Saskatchewan, and attribute it. So you do get some that are not quite right because they're actually from someone who happens to be outside of your bounding box, but it doesn't know that based on the information available, so it just attributes it as being in Saskatchewan. So it errs on the side of including them in short. Okay, but we're getting quite a few tweets here from the province. Okay, so this is filtering by geography, by a bounding box. But I want to again emphasize a few things. First of all, we could have many bounding boxes. It's not just one. We could have several. Secondly, so up to 40, I think. So that would allow us, for example, for provinces with more complicated shape, we could piece together bounding boxes that would show them, form collectively a decent approximation to its shape. The second thing is we can do more than follow by geography. We can follow by user, and we could follow by keyword. And so, and I think conjunctions of them. So we could follow Saskatchewan tweets that are about vaccination, or Saskatchewan tweets about emergency rooms, or Saskatchewan tweets about chickenpox or something like that. Okay. I'm troubled. Just the Scala part of me is really troubled by this. I don't like what's going on there. So I'm going to. So now we're having this go on. I'm going to press Control Z and I'm going to terminate it. Okay. Number 1, and I terminated my Spark shell. Now I'm going to go into Scala. It's it's not there. It's not on that machine. It's here. Fine. I'll call it up in my Scala shell. And in fact, we're not even going to need to be on 898 anymore. We sort of exercised our things there. So I'm just going to go into Scala. I am going to create the same def in Scala here. I just want to see if we could do this more elegantly. It's really bothering me. I think at least Dorian here will understand the angst I'm feeling. The question is, can we do, yes, there. That would have been the thing to do. That would have been much more elegant for way of doing this, I think. Or at least it's more transparent. So we want to do dot flatten, and then we could have just called this like that. This is going to basically flatten it into a single list. That's how Twitter wants it. This semantically describes what it is, but this is how it wants it flattened into a list. So if you had more than one bounding box, it would just put them one after the other in the list, okay? So I just did flatten here, and then I just can call this from here. And by by Scala convention, I don't even need the open parent, end parent, but I'll put that there for clarity, okay? Probably would even be better just to use the constructor. Anyway, okay. So that's Twitter filtering. Are we okay with that? Okay. I'd like to switch now to Zeppelin. We're going to go through the latter half of this lecture, which is going to focus on state maintenance, okay? You've seen basically Twitter filtering, which provides a way of more efficiently gathering tweets that match a certain criteria on an ongoing basis and processing them. But now we're going to look at a somewhat more advanced mechanism in Twitter, in tweets that are going to allow us to keep track of accumulating information, even though we're dealing potentially with many machines and we're updating it on an ongoing basis. And for this, I've also posted something to the Moodle site. It's a JSON file, okay? And you can find it under March 22nd, Spark streaming with state-based methods, function addressing serialization need. Okay. I have a certain impulse to refine my code. And last night, I think it was around 11 or something, I said, I don't like having them do it with an object. Let me see. It's much more elegant with a function. And I was correct in my surmise. Yes. Okay. Okay. So, ladies and gentlemen, you're going to need to go to Zeppelin, and you need to import the note, choose the JSON file, and go get your go get that JSON file and load it in. I'm going to switch over to it. There we go. 22nd, function addressing serialization needs. Here we go. Yeah. Okay, so have you folks loaded that? A little bit more time? Do you need more? Who would like a little bit more? Okay. Okay, so what I'm going to do is walk you through this code. I didn't want you to have to enter it yourself like the earlier code, so we're going to walk through it. First thing we're going to do is we're going to import a SWAC of libraries. Okay. Now, what's notable in this library is that we're going to import an atomic integer. Okay. Atomic integer is a mechanism to encode an integer, but in a fashion that operations on an integer are guaranteed to be atomic. What do I mean by that? They're guaranteed to be atomic.
They either complete totally or not at all.
It's as if they don't complete at all. That's right. And more than that, well, yes, and so they observe here a very nice property by extension of that if there's two different computational units, say threads, say different machines that are modifying it at the same time, either one will go before A will go before B, or B will go before A. From A's standpoint, it's as if B hasn't done it yet or has done it completely. And so we won't have a situation where A reads the number to update. It wants to, suppose both A and B want to add 1 to it. We won't have a situation where there's a race condition where A reads it, B reads it. They both read 100. A goes to update it to 101. B goes to update it to 101. By the time B updates it, A already overrode it with 101. And now B updates it with 101. And both of them tried to update it, but only got updated by 1. Should have gotten updated to 102. But because there was this race condition, because B saw it halfway through A's operation, halfway through, it had read it, but not yet updated it, B doesn't update it with the, it's not atomic in that case, in which case, B will update it with a number that's not proper. There's a whole theory associated with this that I don't have time to go into, with concurrency mechanisms and safe concurrency, and just suffice it to say that atomicity is a property that can be guaranteed by Spark on a broader context of multi-threaded and distributed computing here. So we're going to have an atomic integer that we're going to use to encode information. Next, we're going to set some logging levels here so we're not surrounded by messages. Now we're going to set up a Spark streaming context, okay?
So, sorry.
Yeah.
So that will only help us if our pipeline has functions where the order in which those functions occur is not important. Because if we Want to add one and divide something?
Correct. Oh, yeah.
Something like that.
Very good point. Yeah. So it'll be dealing with cases where we have different computational units working on the same mechanism, and we don't care which of them go first or last. We're not going to use it. What we're not saying, Dorian, there is that all operations, we don't care what order they're coming in. We're going to use it for very specific contexts of, we have different computational units working to undertake the same task, and we want them to be properly brokered so that one goes before the other or vice versa. There's not this kind of awkward race condition where they can lead to a state that's inconsistent with both having been executed. Yeah. Okay. Now we're going to set up the Spark streaming context, and maybe for didactic purposes, what I will do is just separate out this into a different little block. You don't have to do that, but I'm doing it for didactic reasons, because this stuff, it should be very familiar to you by now. We set up a streaming context. This is the Spark context, and we set it up to go with a certain number of seconds per update. We've done this many times now. What's new is this next thing. Having derived the Spark streaming context from there, the streaming context, we're going to need to put in place some mechanisms that will allow it to maintain this state in a safe, robust way. And this is through a mechanism called checkpointing. Okay. And checkpointing will support this atomic sort of abstraction that we want to maintain here, and it will allow us to provide these guarantees involving the concurrency that we want to ensure. So we set this up here to have a checkpoint, and we indicate where the information for that is maintained. And then we extract a tweet stream. Having set up the Spark context to use checkpointing and so on, we're going to create a tweet stream. Now, this next one is going to be where we set up some atomicity. So we're going to have a count of iterations here, okay? And these are really at two different levels. I don't want to put them together. We're going to have a count iterations per safe report, which is just going to be a thing. How often do we print out reports on what we've gotten in, and or put them up to disk? But this next one is going to bear more consideration, because we're going to have a count of iterations that is going to be incremented across multiple machines. Okay, this is going to be an atomic integer that we're going to be incrementing down here. We're going to use this get and add in the later features of this. Get and add is an atomic operation. It gets the value, and at the same time, it increments it in an atomic way. So no other machine can sort of read it halfway through when it's been, gotten but not yet incremented. Okay. So we're going to use this count iterations as if it's an integer, in the sense that we're taking it modulo things, but we're going to manipulate it when we actually got to change it in a way that reflects its atomic status. So we're going to use this get and add. Okay, so this is a atomic integer here, and now we're going to put in place some of these key mechanisms that are going to be used for state-based management. So fundamentally, we're going to need a way to put in place a mechanism for combining a running total count of the number of times we've seen a place or number of times we've seen a phrase. We're going to keep track, like how many times have we seen a tweet from Saskatoon? How many times have we seen the phrase doctor in our tweets? And we're going to have a running total at any given time. We're going to say we've seen this many. But what's going to happen is we're going to have new values that need to be accumulated into that come about as new tweets come in. We're going to have tweets which mention doctors, and we're going to need to process them and add them into our running total. Okay, here we're going to have a sequence of integers. We might have 0, so we're going to use get or else here, or we might have excuse me. The get or else is because we have the option here. When might we have no value here? When might we have none? Well, if we haven't seen any yet, it's going to be none. Okay, and so we get or else 0, and we add to it the values that have just come in. Okay, and we'll see where this new values from keys will be coming from. These functions will be used in a minute. But fundamentally, we're going to be getting new values from the tweets, and they're going to need to be harvested from a lot of different machines, potentially. Okay, different processing units. Okay, now I've created, and this is where we avoid the synchronization issue. I've created a filtered tweets by a specified filter. So here we have a curried function. We specified a dictionary that specifies the values to be used, and then we have a tweet stream, and it's curried. So we first specified the dictionary, and that's going to give us back a function whose job in life is to filter a tweet stream by that, using the phrases in that dictionary. Okay. We've avoided synchronization here because we've passed in the dictionary rather than just referring to it externally. If we referred to this, instead of saying dict here, we referred directly to key phrase map, we'd encounter a synchronization error because it'll be referring to something that's tangled up with the surrounding context, which we don't see, and it won't be able to synchronize it. But here, because it's referring to just an argument, it can synchronize it fine. Okay, so this is a very similar thing to what we did last time. And the basic mechanism here, if you're having trouble reading the parsing it, basically we get the text from the tweet. We are then going to save away the full tweet information, but we're going to go extract those keywords here, which appear in the text of the tweet. Okay, so that's what this is getting. It's filtering to only include those keywords from this thing here which appear in the tweet, and then we're going to go and only include those tweets which have matched at least one keyword. Okay. So we've matched up a single keyword here. So in other words, the set of these keywords that we've matched is of size greater than 0, or the set that resulted from this filter. Okay. Okay. So that's how we're going to filter by these things, and I'm going to call this key phrase map here to just get that in place. And then we're going to create, through currying, we're going to create a function whose job in life is to filter by this key phrase map. We created this function through currying. By passing it the dictionary, we got back a function which takes a tweet stream and is going to filter that tweet stream according to this logic here. In other words, it'll filter out those that do not include keywords. Okay. Great. Now you'll notice that what comes out of this tweet stream is actually a D stream that includes two things: status and a set of strings. What is a set of strings? Why is there a set of strings here? What is that set of strings? It's a set of what? Of the keywords. The keywords in here that matched. So it's actually remembering the keywords that match this tweet. What is status? Yeah, this is the tweet. This is the full information about the tweet. So we've bundled into this. What this is recording is it's giving us back a D stream of, it's taking a D stream of statuses alone, and it's giving us back a D stream of statuses and the set of strings that they match, but limited to those statuses that match at least one keyword. Do you see that? So we get back up. It's a pared down set of these tweets, a pared down stream of these tweets to only include those that match at least one of these. But we're also recording which ones of these we matched, right? Yeah, believe me, the logic with this was fun to think through. Okay. Okay. Next. Now, this function whose job in life is to filter by the key phrase map, we're going to apply it to tweet stream. What are we going to get back? Tweet stream is a stream that we created way up here. Where is it? Where is it? Here it is. This is a plain old tweet stream of a D stream of status. And what are we going to get back by applying our function to it? What are we going to get back here? We're going to get back, yeah, a filtered thing that includes status and the keywords by which they match. So having done that, we are then going to we're going to map them. And what is this one doing? Well, it's only extracting the first element of that, which is the tweets itself. So we're separating out the tweets. Unfortunately, we can't unzip it. Man, if we could only unzip these streams, that'd be sweet. We just unzip it into two pieces. But here we can extract the tweet part, and here we'll deal with the key phrases. This is the set of phrases that they matched, right? Because remember, each of these matches, each of these guys is returning a status and a set. And so here we're separating them to their two constituent components. So interesting tweet stream is a stream of what? That's a stream of status, right? The flattened key phrases stream is, I used flat map on it. So guess what? It would have been a set of statuses, a D stream of statuses. But now because I've used flat map, it's a D stream of what? Sorry, it would have been a D stream of set of strings. And instead, because I use flat map, it's a D stream of strings, which is sort of the set of keywords it's matched, or the set of, they're actually regular expressions that it's matched, right? These are regular expressions, right? They're not just any old keywords. They're like things saying, okay, it's sick, but it's got to be sick with no letter in front of it. So it can't be homesick, right? And similarly, ill has to occur as its own word, etc. Okay, so So we're going to have a stream of those. Okay, watch that. Wow. Okay, now this is where some of the action happens. Okay. So this is going to come pretty thick and fast. So we got to pay attention to it. Okay. So, ladies and gentlemen, before, you may remember, we defined some functions. Basically, these functions, their job in life is to combine new counts of occurrences of like a reference to a place with a running total that's an existing count. Okay? So we have an existing count, and we're going to combine in some new counts which occurred in the latest round, and we get out a single number. And how do we get out that single number? Well, the single number is an option, and it's the sum of the new ones plus the old one, okay, where we treat it as 0 if we haven't gotten it anymore. Does that make sense? Okay. Similarly for key phrase. Now, we're going to use that here to maintain state, okay? So update state by key is basically going to update a stream of keys and values. Okay, now that key value stream that we have here, the keys in it is going to be these key phrases that we're looking for. The value, what do you think the value is going to be? Yeah, number of occurrences thus far. Cumulative, not just in this current batch of tweets, but cumulative. Similarly, for place, we're going to engage in some frobbery, but basically we're going to try to get the place and map it to a full name and deal with cases where it doesn't exist by wrapping it in an option here. So we'll deal with it as none. It's just none if it doesn't have these things, if it doesn't have a full name. Okay, and it's going to be a count of 1 for that. Okay, so we're going to go. So, and we're going to print those out, those streams, or we're going to be updating this place count stream, and then we're going to also print out the interesting texts themselves. The interesting texts are from this interesting tweet stream, and the interesting tweet stream, you may remember, is something that we got. Okay, where's my interesting tweets stream? Here it is. It's right here. It's just the tweets that passed. They had at least one of these keywords in it, right? At least one of these keywords. Obviously, we could have filtered them by other things too, like if they were retweeted by a health authority or something like that, we could have included it by that or whatever. So I'm going to execute that. Now, so this is getting all of our ducks in order. This interesting text stream, this is just a stream of text. You can look at the types here. This is a D stream of string. Okay. Next. This you don't have to do. And I would suggest, unless you're interested, I hemmed and hawed about this because I thought some people might be really interested to see how it's saved as text files, but it's some added logic. You don't have to execute it, but basically what's happening is we're saving things as text files, and this get and add for the atomic int, what that's doing is it's allowing us to know, to cognizant of the fact that it's being executed across potentially many machines, how many iterations have we counted on whatever machine out there, so that we know when to save things away to a file. And this repartition 1, again, consolidates all of the data to a single partition, to a single location, so we can put it out all into one file. Okay? You don't have to execute that, but if you want to, you could go see your interesting tweets and place count saved away. And what remains for us is to start and let it terminate, okay? Now, this is an interesting little example. What you will see is tweets coming in that will contain these keywords, right? These key phrases, these regular expressions. And you'll see them cumulatively sort of being listed, and you'll see the tweets themselves that are interesting, that contain them there. Okay, so a very important thing to parse what's going on here. So this printing is occurring from these 3 print areas, and each of them prints out the time as well. Okay, I think this is Unix time. Each of them prints out the time. So all these are from the same time. You see it all matches up. So just each, when you print the tweet stream, it prints out the information. Mind you, this is a tweet stream. What? It's a tweet stream? Yeah, it's a tweet stream. Those counts are in a tweet stream, ladies and gentlemen. These counts, the results of this update state by key, is this updated phrase key count state KV stream. Where is that? Updated phrase key phrase count KV stream. Here it is. It's a D stream of strings and ints. Okay, that's what that is. We're keeping track of it here, and we're using these functions. You may remember this interest. We got that from. Sorry, where are we? Here we got this put together using this function, which is basically allowing us to produce this stream of counts thus far using this combination mechanism, right? Each new one, it's combining in the counts from new ones to our running total, okay? And this is allowing this sort of running count to be maintained. So you can see, you could see like it's finding, okay, illness is here, sick. Okay, I guess this is sick. It's unclear that it's in a health context. And here's sneeze. It's about cat sneezing. Okay, I apologize for showing tweets that aren't always put together in most appropriate English. Okay, here we go. So here's the next time. There's nothing new. Here we go to another time. Okay, now it's finding one that for doctor. It found doctor here. Okay, so it's keeping this running count as a stream. Whose values are being computed by this update state by key and update keys by key. It's automatically accumulating these things, right? He's sick of the snow, right? So we've got more, and then we've got sick coincidence, right? So we're getting a lot of sicks, but with limited health significance, right? And so it is. And as we go on, we get more and more of these, and they're accumulating things across multiple languages and so on. Okay. So ladies and gentlemen, this is state-based updating. The key point is that we are able to maintain a running total, something that is sort of computed as a stream using these mechanisms in a way that's atomic, in a way that draws on data from across many processors, across many computational units, distributed machines, but gets out a unified stream that we can then save away, record, etc., to keep track of totals. And that running count is a string. Okay. That's that mechanism. This mechanism for keeping track of keys and values is actually pretty core to Spark. So there's a lot of support, particularly at the RDD level, the resilient distributed data sets, for maintaining key value pair data sets. Okay. And this Spark streaming maintains this for good reason. And it's a reflection of the fact that in the big data era, there's quite a lot of computational infrastructure, a case in point being Cassandra, for example, which are key value databases, or store things in a key value fashion. And here we have key value streams. Okay. So I'll just talk. That's all for these details today. Maybe what I'll do is I'll switch back to stop the sharing, and I will just finalize my lecture by saying that during our next series of lectures, probably it's going to take us the remaining 4 lectures, I'm going to be going through a new topic and covering Spark. The topic is the use of the machine learning interface for Spark in its 2 forms. One is the older ML library, which largely operates on resilient distributed data sets, and has support for quite a number of machine learning algorithms. And the second is the more modern, more sophisticated, and higher level ML library, also built into Spark, which can operate on data frames, data sets, typed and untyped. It can support explicitly defining higher level abstractions like pipelines for machine learning analyses. And these pipelines are going to draw on some of the first things we talked about in this course. Successive filtering. We've done some of that here. I mean, in today's discussion and previous ones, I mean, we have these successive filters of things, maps, etc. But here, we're going to be seeing, we reify these pipelines as objects with transformers and actions on them. And we are going to, by virtue of doing that, be able to compose them. So you can have pipelines that are put into as parts of larger pipelines, and where we're going to be able to compose sub areas of the pipelines for things like calibration, or so to train a model, and other things to test a model. And we're going to build up this pipeline out of those pieces, and then potentially use it in larger pipelines. Yeah. So we're going to see that these pipelines provide us a really convenient way to describe at a high level machine learning operations. Do so in a way that taps into distributed computing resources, but also do so in a way that's very clear conceptually as to what's going on, and extraordinarily flexible. We're going to be able to take similar pipelines, modify them just a little bit, and use them for very different types of machine learning algorithms conceptually. Things like we might use a classifier that's a naive Bayes classifier, and then we might instead put in place a classifier based on decision trees, decision forests, then put in place a classifier that's based on support vector machine. And we can do that very, very easily using the same basic mechanisms, okay? Train, test, similar data sets, and it will take care of a lot of the gory details that if you're programming something like R, you got to really sweat with more detail focus. So anyway, that's where we're going the next 4 lectures. If any of you want to take a peek at that, there are lectures from last year that this will be drawing on. They were connected with the shell, the Spark shell we saw today, rather than in Zeppelin. And I'm going to be modifying them for Zeppelin, so we can do interactive graphics and stuff like that. But the basic mechanisms you'll get to see pretty well from last year. Okay, so if anyone want to do that, that'd be great. And I think what I'm going to do is to put out an exercise for you to work on over the weekend that will be Spark streaming based, and it's going to involve Twitter, a filter by something other than location, okay, namely by keyword, and we're going to see how that can be used, okay, and we'll talk about that some on Tuesday. Good, thank you very much, and we're ending early for once. It hasn't made up for the cumulative deficit, but we're working there. Okay, thank you.